Well, welcome back to our course on systems engineering. And for this lecture, we're going to be talking about systems integration. And so just to give context, we have gone through a couple of sections of foundations of what system engineering is all about. We talked about the front-end development with concept development. Then we're slowly working through the engineering development. And so this is going to be the fourth of 5 lectures that we'll have on the engineering development. So relatively speaking, this will not be too long of a recording, too long of a lecture, but hopefully you'll get a chance to get a better sense of what system, what the whole purpose of this is, system integration. So let's focus first with integrating the total system. As the name implies, the integration phase has the objective of assembling and integrating the engineered components of the new system into an effectively operating whole and demonstrating that the system meets all of the operational requirements. The goal is to qualify the system's engineering design for release to production and subsequent operational use. As previously noted, the system engineer lifecycle model defines integration as a separate phase of system development because its objectives and activities differ sharply from those of the preceding portions called the engineering design phase. These differences are also reflected in changes in the primary participants engage in carrying out the technical effort. If all of the building blocks of a new system were correctly engineered, and if the design was correctly implemented, their integration and subsequent evaluation would be relatively straightforward. In reality, when a team of contractors develop a complex system during a period of rapid evolution at evolving technology, the above conditions are never fully realized. Hence, the task of system integration is always complex and difficult and requires the best effort of expert technical teams operating under system engineering leadership. Hence, the integration phase may begin with very considerable preparation remaining and may therefore proceed considerably slower than originally planned. The purpose of what we're talking in this lecture and the chapter that we're relating it to is to describe the essential activities that are typically required in this phase, a number of problems that are commonly encountered, and some of the approaches to help overcome the resulting obstacles. Additional topics such as agile system engineering, human factors, and system engineering are also addressed with respect to the integration process. Well, first, let's come back to this familiar diagram here where we're considering the place of integration in the system life cycle. So the figure we're showing has 2 different aspects of the relationship between the integration and evaluation phase and its immediate adjacent phases in the system lifecycle. The figure is a functional flow view, which shows the integration phase to be the transition from engineering design to production and operation. Its output from the engineering design phase are an engineered prototype, including components. The outputs of the integration and evaluation phase are system production specifications and a validated production system design. The difference in the primary objectives, activities, and technical participants of the integration and evaluation phase from those of the engineering design phase are summarized next. And so let's go at them one at a time. First of all, we have the program focus. The engineering design phase is focused on the design and testing of the individual system components and is typically carried out by a number of different engineering organizations, with systems engineering and program management oversight being exercised by the system developer. On the other hand, the integration phase is concerned with assembly and integrating these engineered components into a complete working system. In terms of the program participants, the primary participating technical groups in the integration phase are system engineering and design engineers. These personnel will represent multiple functions and disciplines of the system, typically organized around components and subsystem capabilities. In terms of the critical problems, the system integration process represents the first time that fully engineered components and subsystems are linked to one another and made to perform as a unified functional entity. Despite the best plans and efforts, the integration of a system containing newly developed elements is almost certainly to reveal unexpected incompatibilities. At this late stage in the development, such incompatibilities must be resolved in a matter of days rather than weeks or months. The same is true when deficiencies are discovered in system evaluation test. Any crash program to resolve such critical problems should be led by a systems engineers working closely with the product manager. Then in terms of system engineering methods in an integration, the integration steps will follow the design of the components as they are developed to satisfy the system requirements. As a functional design of the system has been completed in previous phases, the functional definition step relates to the integration facilities. The physical definition of synthesis steps correspond to subsystem and system integration. The components have been implemented in previous phases. Then thinking about the systems integration, the typical activities that take place include integrating the test components into subsystems and the subsystems into a total operational system by sequential aggregation and testing of the constituent elements, and designing and building integration test equipment and facilities needed to support the system integration process and demonstrate end-to-end operation. In terms of agile system engineering and integration, systems being developed with an agile approach will experience a number of integration efforts in the sprint cycle as they are developed, integrated, and tested. This approach will provide potential users many times to evaluate the additional progress and capabilities since the last sprint in order to test and provide feedback. As the agile principles strive for a continuous integration, it will be dependent on the development team to determine their desired integration and testing periodicity. For small projects, this may occur daily, and for large projects, this may occur weekly. During the Scrum is where coordination should be planned and resources allocated if the integration effort requires additional staffing or attention. Attention should be paid towards planning near-term and far-term integration efforts and the implication that it may have on the overall system development. Well, let's give an overview of the system integration approaches. There's three. So the three main approaches taken when integrating systems, which will require a system architecting and overall plan to follow during the system development. These approaches are top-down integration, bottom-up integration, and what's called big bang integration. So top-down integration, starting with overall system concepts and decomposing them down to subsystems and component levels. While bottom-up integration, what it does is it's starting with the components and forming into larger groups such as subsystems and ultimately the system. And then we have the big bang integration where all elements are provided and then integrated, typically works best for small scale and less complex interfaces. Well, we'll also talk about system integration planning and facilities. We'll have a couple of diagrams to explain this, but just give some orientation to begin with. In the engineering of a new complex system, many integrating components, integration at the system level cannot begin until the system has been fully assembled and demonstrated to operate as a unified whole. There's a high likelihood that some of the interfaces among the elements may not fit or function properly, or that one or more interactions among them may fall outside prescribed tolerances. Thus, experience has shown that no matter how thoroughly the individual components have been tested, there almost always remain unforeseen incompatibilities that do not reveal themselves until the system elements are brought together. Such discrepancies usually require changes in some components before the integration system works properly. These changes in turn frequently require corresponding alterations in test equipment or procedures and must be reflected in all relevant documentation. So in the section, in this part of the lecture, describes the general process and problems involved in integrating a typical complex system. The successful and expeditious integration of complex system depends on how well it has been partitioned into subsystems that have simple interactions with one another and are themselves subdivided into well-defined components. The integration process can be thought of as a reverse of partitioning. It is normally accomplished in two stages. One, the individual subsystems and are integrated from their components, and two, the subsystems are assembled and integrated into the total system. At intervals during both stages, the assembled elements are tested to determine whether or not they fit and interact together in accordance with expectations. In the event that they do not, special test procedures are instituted to reveal the particular design features that needs to be corrected. Throughout the entire process, system integration proceeds in an orderly, stepwise manner, with system elements added one or two at a time and then tested to demonstrate proper operation before proceeding to the next step. This procedure maintains control of the process and simplifies diagnosis of discrepancies. The price for this stepwise integration of the system is that at every step, the test equipment must simulate the relevant functions of the missing parts of the system. Nevertheless, experience in the development of large systems has repeatedly demonstrated the provision of this capability is, in the long run, quite cost effective. In the integration of large software programs, this is frequently done by connecting the program executive to non-functioning modules, which are successfully replaced with one at a time by functioning modules. Determining the most effective order of assembly and selecting the optimum test intervals are critical to minimize the effort and time needed to accomplish the integration process. Since both system level knowledge and system expertise are essential in the definition of this task, the task is normally assigned to a special task team comprised of system engineers and test specialists. Well, as we're doing system integration, the first thing that we have to do leading up to that is subsystem integration. So we'll look at this figure and talk about this before we get into the next level. So as noted previously, the integration of a subsystem from its components parts is normally a stepwise assembly and test process in which parts are systematically aggregated and the assembly is periodically evaluated to reveal and correct any faulty interfaces or component functions as early as in the process is practical. The time and effort required to conduct this process is critically dependent on the skillful organization of the test events and efficient use of facilities. Some of the most important considerations are discussed below. And so we'll talk about them next. And so the order in which system components are integrated should be selected to avoid the need to construct special input generators for simulating components with the subsystem, that is, other than those simulating inputs from sources external to the subsystem being integrated. Thus, at any point in the assembly, the component that is to be added should have inputs that are derivable either from generators of external inputs or the output of the components previously assembled. So this approach means that the subsystem integration should begin with the components that have only external inputs, either from the system environment or other subsystems. Examples of such components are 1, subsystem support structures, 2, signal or data inputs, and 3, subsystem power supply. The application of the above approach to the integration of a simple subsystem is illustrated here in the figure, in which the subsystem under test is composed of 3 components. The configuration of components in the figure is purposely chosen so that each component has a different combination of the inputs and outputs. Thus, component A has a single input from an external subsystem and two outputs, one an internal input to B and the other to another subsystem. Component B has no external interfaces, getting its input from A and producing an output to C. Component C has two inputs, one external and the other internal, and a single output to another subsystem. So the special features of the test configuration are seen to be one, a component compound input generator to provide the two external inputs to the subsystem, one input to A and the other input to C. Internal test outputs from the interfaces between A and B and between B and C. These are needed to identify the source of any observed deviation in overall performance and are in addition to the external subsystem output from A and C. And three, a compound element model containing the functions performed by the constituent components and providing the predicted output of the test interfaces. So the following integration sequence described above with the configuration that we're showing in the figure would be assembled as follows. And so we'll first start with A with no internal inputs, the A's outputs. When we test the A's outputs. 2, we add B and test its output. If faulty, check if the inputs from A are correct. And then 3, we add C and test its output. The above integration sequence does not require the construction of input generators to provide internal functions and should rapidly converge on the source of a faulty component or interface. The approach described above works in the great majority of cases, but must, of course, be carefully reviewed in the light of any special circumstances. For example, there may be safety issues that make it necessary to leave out or add steps to circumvent unsafe testing conditions. Temporary unavailability of key components may require substitution or simulation of elements. Particularly critical elements may have to be tested earlier than in an ideal sequence. System engineering judgment must be applied in examining such issues before defining the integration sequence. Well, let's think about total system integration. The integration of the total system from its subsystem is based on the same general principles as those governing the integration of individual subsystems, which were something we just spoke about. The main differences are those of relative scale, complexity, and hence criticality. Faults encountered at this stage are more difficult to trace, costly to remedy, and have a greater potential impact on overall program cost and schedule. Hence, more detailed planning and direction of the test program are in order. Under these conditions, the application of system engineering oversight and diagnostic expertise are even more essential than in the earlier stages of system development. Then in terms of the system integration test facility, which is one of the things we'll be getting into in more detail in a little bit, it was noted that special design facilities are normally required to support the integration and test of systems and their major subsystems. This is even truer for the assembly and integration of total systems. Often such a facility is gradually built up during system development to serve as a test bed for risk reduction testing and may be assembled in parts from subsystem test facilities. As in the case of subsystem integration test facilities, the system integration facility must provide for extracting data from test points at internal boundaries between subsystems as well as from the normal system outputs. Should also be designed to be flexible enough to accommodate system updates. Thus, the design of the integration facilities need to achieve the necessary test conditions, measurements, and data analysis capabilities is itself a major systems engineering task. We also have the idea of system of systems integration, not just one system, sometimes called SOS. So system of system integration can be similar to a single system integration approach, but different in certain ways. The similarities are the interfaces between elements are still remain and still be concerning with units, timing, and understanding. Integration, planning, and collection of skill sets will occur similar to the single system, although it will encompass additional companies and organizations that are involved with each system. Sometimes the synergy of engineers can provide a unique or more efficient perspective that can benefit additional systems that are involved. Where this may differ in system of systems is the lack of transparency and understanding inside of each system. Think of integrating a series of black boxes. We'll know the interfaces between the boxes, but we do not have the insight in how they were internalized and comprehend the information passed over the interfaces, and may have to rely on the outputs that the system will pass on the next connected system. As each company or sponsoring organization is in charge of their individual system, there will likely be additional coordination between the system effort in order to get the system of system fully functional as the integration phase progresses. Funding for individual systems, if not provided by the system of system effort, may affect the rate of change and responsiveness of each individual system in order to satisfy their integration obligations. Okay, we'll have a single chart for each of the three integration methods, and we'll go through them one at a time, and we'll also give a little bit more context to start out with. And so that beginning context is we'll just be thinking a little bit more of the types of integration. System and integration can take several different approaches: top-down, bottom-up, and big bang. Each one is discussed in the textbook, and we'll get a chance to have insight into the advantages, disadvantages, efficiencies, resource demands, and dependencies for each. So it's up to the systems engineer, program manager, and stakeholders to agree on the integration approach based on the desired objectives, schedule, available budget, and desired end state of the system. Let's start with a top-down integration. This approach starts with a high-level system concept and then decomposes into smaller units. This approach can provide a high-level look at the entire system concept from the beginning, and then incrementally build in additional levels of detail as the project progresses, which can provide users and stakeholders a view of the bigger picture from the beginning. However, this approach will require numerous stubs to be built until the last level of system detail is developed. This approach will require system architecture to be followed, as the integration test and exit criteria will need to be developed as the project continues. Specific skill sets for lower level system elements will need to be sought out when it is time for them to be developed. Integration facilities can be planned for as the various lower level elements are developed and shown, and should be considered when the integration schedule is being developed. So the figure also provides an overview of the top-down integration process, and we can be seeing those steps laid out. Well, next, let's talk about the bottom-up integration approach. This approach is much like many of the system engineering textbooks teach. Each of the design configuration items is then aggregated and integrated into components. Groups of these components are then integrated into subsystems, which in turn are integrated into the top-level system. This can follow a methodical approach to ensure that all elements of the system are accounted for, and rework can be performed until the successive level is satisfactorily constructed and integrated. This approach requires a system architecture to be followed to ensure that the requisite elements be included in the integration build, which can include fairly well-defined integration tests and exit criteria to determine when the next level of capability is developed. However, the full system capability is not realized until all of the builds have been completed and integrated. Integration facilities must be determined based on the elements that will be integrated, but also consider the skill sets of the lower levels needed for consultation. And so what we're showing in the figure, it provides an overview of the bottom-up integration process. And we can also see the steps laid out along on the right. Well, we'll finish up this lecture with a few more topics. First, we'll go over the third integration approach. We don't have a chart that shows that, and then we'll be talking about different aspects of integration and have a few more specifics when we're talking about the facilities. So for the Big Bang approach, this approach is sometimes referred to as the global integration, as all the elements are integrated in a single step. The feedback is immediate to determine if the integration is successful, and little planning is required for the integration. This approach may be difficult to show where any integration faults reside within the system configuration after the assembly. This approach is good for systems that do not have a large number of components, and subsystems have simpler interfaces. Similar to other integration approaches, the system engineers can collect and assemble the elements by availability, incremental, or by common attributes that may require some additional attention to the assembled subsystem. Okay, well, now let's get into integration planning. As with any part of the system engineering projects, good planning can help avoid pitfalls and keep the project on schedule. Some of the considerations for planning may include overall technical integration plan, planning for adequate quality assurance resources when the integration efforts will be executed, proper personnel training, subcontractor management with regards to dependencies, quality, and interfaces, risk assessment during the integration efforts, audit trails, and evaluation of the performance based on the integration efforts. Other considerations for planning may include location of facilities, type of transportation needed for component and subsystem to the high-level integration facilities, type of skills needed, and communication between components, resources, staffing, and special constraints on the facility itself. Correctness of integration is also an important concept in order to ensure the integration is completed properly. As this may seem intuitive, a review of the following items is helpful to verify within the integration phase the correct integration plan is followed. The integration timeline allows for sufficient time to perform the work. All components and configuration items are accounted for. All interfaces are identified and verified, and all tools and procedures are available, and all work is documented. Well, lastly, we'll talk about integration facilities and some sub-concepts related to that. As a system concept is being developed, system engineers must identify locations for integrating these system components, regardless of the approach taken. Several considerations are provided, we'll talk about below, for the detailed elements of software, hardware, and human factors as an example. Based on the systems engineering project, location of developers, integrators, testers, stakeholders, users, and manufacturers will drive decisions on where to perform the integration. Sometimes the project will make these decisions based on the lead system integrator, who will be responsible for the overall integration efforts of the systems. Sometimes the integration and involvement may be out of the system engineer's control, as many states will provide parts for the system. Many large-scale defense-oriented projects will have this as an example, which may force regional or subsystem integration clusters based on technical dependencies or distance to travel. Well, let's talk about the three related areas. First of all, for software integration facilities, software modules can be integrated in different locations, either at the main developer site or at various subcontractor sites. Common interfaces and units should be followed in order to ensure that the proper flow of action and expected outputs are achieved. Software architecture types will also help dictate the amount of integration needed by defining the interfaces, units, modularity, and logical limits that would be used during the development. Through the use of architecture views to show different user perspective, the software engineers gain an appreciation on how to develop the software. Software may be developed concurrently with the hardware and human factors and integration based on based on the project approach. Next, we have hardware integration facilities. Systems may be constructed from multiple subsystems and components, either in the same facility or multiple facilities and locations. Receipt of the input will first be inspected and accepted for integration. Use of common interfaces for physical integration is likely to promote standardization and ease of integration. Predetermined by the specification for each of the designers to conform to. Depending on the type of integration, there may be either serial or parallel integration efforts when constructing the system. Serial integration relies on the dependency from the previous integration phase, from being successful prior to progressing through the current step, which can catch errors, but will also progress as fast as the phase will allow. Parallel integration can decrease the time for overall integration, but will require additional quality assurance resources to ensure that errors are caught and proper integration of the system is achieved. It's up to the systems engineer and program manager to determine the best approach. Other factors contribute to the decisions, may include physical space to perform the integration, time and schedule constraints, and the amount of transportation of the components and subsystems, if located in different facilities. The textbook refers to Browning's work with the design structure matrix. And states it provides a good visual to identify the connected components of a system in order to determine common grouping of components and potentially discover a more efficient means of system assembly and integration. The design structure matrix, or DSM, can be static or time-based. A good application of this approach is for automotive assembly, where the components of the car must be assembled into subsystems and eventually into a single system. By using a DSM and identifying the different inputs and outputs of each of the components, one can reorganize the assembly into a more efficient process by grouping similar components first before integrating with other subsystems. Finally, just a short discussion on human factors integration facilities. There are numerous industries that will take into account the human user in order to integrate their system features. Defense, aerospace, and automotive are just a few examples. The automotive manufacturers will consider the human when incorporating concepts such as autonomous driving, system entertainment, or ergonomic factors to enhance a user experience. Subsystems specifically designed for humans users may be located in different facilities in order to evaluate how different combinations of the capabilities and components will produce the best outcome. Subjects participating in these facilities would have knowledge of the current operations and provide a representative baseline of the operational community. They would also be aware of the newer system capabilities and be able to provide critiques of how well that the new system either enhanced or detracted from their capability to perform the system objectives. This comes with some caution, as a small percentage of the population may or may not be completely representative of the future generation of operators. Integrating with a wider pool of applicants can help to alleviate this situation. This may also occur with multiple system types with human factors. Obvious examples are defense-oriented, where operators could represent different services or different systems while evaluating the integration efforts. In these cases, local interpretation of the situation may be different depending on the system's capability, providing different responses. Integration efforts for the entire system may be needed to determine if all systems receive the expected data as well as the understanding of the information. Okay, well, let's finish up with a summary review. There's three major things that we talked about in this chapter, in this lecture. The integrating the total system. The objective of the integration phase are to integrate the engineered components of a new system into an operating whole and demonstrate the system meets all of the operational requirements. The outputs of the integration phase are validated production designs and specifications, qualifications for the production and subsequent operational use. The activities constituting integration are integrating the tested components into subsystems and the subsystems into operational system by sequential sequential aggregation and testing of the constituent elements, and designing and building integration test equipment and facilities needed to support the system integration process and demonstrate end-to-end operation. We also talked about system integration approaches. Three main approaches are taken when integrating systems, which will require a system architecture and overall plan to follow during system development. So those approaches are first, the top-down integration, starting with an overall system concept and decomposing down to the subsystem and component level. Second, the bottom-up integration, starting with the components and forming into larger groups, such as subsystems and ultimately the system. And finally, big bang integration, where all the elements are provided and then integrated, typically works best for smaller scale and less complex interfaces. Finally, we talked about system integration planning and facilities. Facilities to perform integration may occur in the same location as the development and testing, depending on the size and complexity of the project. If the system is a large-scale effort that involves different companies and countries, there may be cultural, organizational, and/or language barriers that must be overcome to ensure that the integration objectives are understood and achieved. All right, well, thank you very much. That's going to end it for this lecture. Thank you.